Esters are my favorite compounds. They smell so good and taste so good. They're found widely in nature as fragrances and flavors. I've pulled together some examples to take a look at. The butyl ester of formic acid is essence of plum. There are a couple esters that are important constituents in pineapple. We've got apricot, rum, wine represented. A couple of different pentyl acetates are important constituents in banana. There are 4 esters listed here that are constituents of apple. I've got cherry, honey, pear, wintergreen, strawberry. Notice the wintergreen and strawberry. They both have the same hydroxybenzoic acid. One of them is a methyl ester. The other one is isopentyl. In any case, you see what I mean. These compounds have great fragrances and flavors. They occur widely. There are many others. These are just examples. Looking at the names of the esters on this sheet, you can figure out how the naming convention goes, but let me go over it with you quickly. This is the ester of butanoic acid. That acid name is changed. So drop the IC and drop the acid. The IC is replaced by ATE, and the ethyl group that's attached to the oxygen is named and put out front. Ethyl's a separate word, ethyl butanoate. If we're talking about this in the common nomenclature, we'd call it ethyl butyrate. Looking at the carboxylic acid that has only 2 carbons, as an ester it will be an acetate. And since this is C4, it's a butyl group, so we'll put butyl as the name that's out in front. This is the alkyl group that's attached to the oxygen, butyl acetate. We know that aromatic carboxylic acids are called benzoic acids, so this will be a benzoate. We've removed the IC and replaced it by 8, and out in front we'll put the isopropyl group, isopropyl benzoate. So if you can name carboxylic acids, it's easy to name the esters. Remember that there are 2 words, and the alkyl group that's attached to the oxygen goes out in front. There are 4 ways to make esters that you should have on your list to memorize. When acid chlorides are treated with alcohols, esters are the product. When anhydrides are treated with alcohols, esters are the product. In both cases, these are standard nucleophilic acyl substitution reactions. And in both cases, the product is favored because you're going from a less stable carboxylic acid derivative to a more stable derivative. In addition, you should have the Fischer Esterification on your list. This is an equilibrium reaction. Every step in the mechanism is reversible. The product is favored because you use a large excess of the alcohol, which pushes the equilibrium way to the right. And finally, there's an SN2 reaction that sometimes is used to make esters, where the carboxylate is the nucleophile, and this needs to be primary or methyl. So the esters have a CH2 group attached to the oxygen directly, or a methyl group. With SN2 reactions, secondary substrates don't work well and tertiary substrates don't work at all. So we prefer primary or methyl substrates. I've shown bromide here as a leading group, but others work too. Both iodide and tosylate would be good choices. So here are 4 ways to make esters. All of them are useful, provide good yields, and offer a variety of different mechanisms. Let me just remind you that esters fit down toward the bottom of the order when we're moving from least stable to most stable, and most reactive to least reactive. So compared to acid chlorides and anhydrides, esters are not very reactive, and they're far more stable. You know that generally you can make more stable derivatives from less stable derivatives, so you could conclude that esters can be converted into amides. True enough, but this typically is a slow reaction that's not used much at all, because you'd far prefer to use acid chlorides or anhydrides. They're much more reactive if you want to make an amide by reaction with an amine. But esters can be converted into carboxylic acids in very good yields. Both basic conditions and acid conditions work. Using aqueous acid, we're looking at the reverse of the Fischer Esterification. So to understand the mechanism of this reaction, all you need to do is examine the Fischer Esterification mechanism. The equilibrium is pushed to the carboxylic acid side by using a large excess of water. The conversion of an ester into an acid using basic conditions is called saponification. Sapon refers to soap, and saponification refers to turning esters into soap. Let's look at the mechanism and I'll show you what I mean. When an ester is treated with aqueous hydroxide, the hydroxide acts as a nucleophile to add to carbonyl. This is the typical first step in nucleophilic acyl substitution, and it's reversible. That intermediate can lose hydroxide to go back to starting material, or it can go to product by losing alkoxide. Because this is done in water, this alkoxide is likely to be protonated rapidly. Notice that this is a catalytic reaction in the sense that hydroxide, which is consumed in the first step, is reformed in this step. But at the same time, it does consume base because the product reacts with base. And this is the reason that this reaction gives such high yields of product. In the presence of strong base, carboxylic acids are completely deprotonated. So saponification is an extremely good way to hydrolyze esters to make carboxylic acid salts in very high yields. If you want to make the carboxylic acid itself, in the end you use strong acid. The yields in this reaction are very, very high. The saponification reaction is used widely to turn esters into carboxylic acids. It's also used to make soaps. Take a look. Animal fats are very special esters. They're esters of long-chain carboxylic acids, typically have 16, 18, or 20 carbons, of an alcohol called glycerol. It has 3 hydroxyl groups. And each of the hydroxyl groups has a long chain attached to it. These are long chain alkyl groups with some double bonds scattered here and there along the chain. And so the glycerol molecule has 3 carboxylic acid derivatives attached to it, making it a triester. And when treated with sodium hydroxide or potassium hydroxide, the products are long chain carboxylic acids. They may or may not be identical. Often they're not. But the key thing is that these are long chain carboxylic acids that in water form micelles. Micelles are spherical clumps where the alkyl chain tails are all stuck in the middle of the sphere, and the carboxylate ion heads are all stuck on the sides of the sphere. So the sphere is soluble in water because of the carboxylate heads on the edges of the sphere. But the center is a hydrocarbon. So it dissolves dirt and grease and things, and that's why soaps and detergents work. The pioneers took animal fats, these carboxylic acid esters. They did saponification with lye, which was a source of KOH, to make soap. There are 2 other reactions of esters I want to point out. One is the same kind of reduction you've seen for carboxylic acids, acid chlorides, and anhydrides. Treatment of esters with lithium aluminum hydride makes primary alcohols. And again, like you saw for acid chlorides and anhydrides, treatment of esters with Grignard reagents adds 2 alkyl groups to the carbonyl. The product's a tertiary alcohol. The first alkyl group adds to make a ketone, which adds a second alkyl group. So these 2 reactions are very much like the ones you've seen before for acid chlorides and acid anhydrides. So in summary, there are 4 reactions you should memorize for esters. Saponification, followed by acid, hydrolyzes esters to make carboxylic acids. Treatment of esters with aqueous acid makes the carboxylic acids directly. Lithium aluminum hydride reduces esters to make primary alcohols. And esters react with Grignard reagents to make tertiary alcohols.